Good day, ladies and gentlemen. Welcome to this presentation on engine cooling, during which we will look at the following aspects. How much heat does an engine produce? Coolant flow and coolant temperature. Airflow through the radiator, temperature of the air through the radiator. What determines the radiator top tank temperature? Typical cooling requirement for a petrol engine. Typical cooling requirements for a diesel engine. Improving the cooling performance of a vehicle. The cooling test. Although this subject can become complex, a pragmatic approach is presented here. The assumption is also that the thermostat is blocked in the fully open position. Right, now how much heat does an engine produce? And the answer is 90 to 105% of the engine power. If we look at the energy breakdown below, from the fuel we see that about 30% of the energy goes to engine power, another 30% to the cooling system, 35% to exhaust heat, and 5% miscellaneous, in other words, radiation from the engine block. This adds up to 100%, and what we see is that the engine power and the cooling system is in the same order of magnitude. Coolant flow and coolant temperature. For a given engine load, the heat load should be considered as a fixed heat source. From the formula Q, which is the heat load, equals M, mass flow of the coolant, times Cp, which is the heat value of the coolant, times delta T, which is the difference between top and bottom tank temperature. Since Q is constant and Cp is constant, it means that if the mass flow is smaller, then delta T must get bigger, so that the terms on the right hand side is still constant. Coolant flow and coolant temperature, we just put it in words again. Since Q and Cp is considered constant, it follows that the temperature difference between the inlet and the outlet of the radiator is only determined by the mass flow of the coolant, and that too big a temperature difference indicates a low coolant flow. Coolant flow and coolant temperature. The coolant flow rate is determined by the water pump speed, resistance in the engine, the head gasket, thermostat opening, coolant flow resistance of the radiator, and the automatic transmission's oil cooler in the radiator's colder header tank. Is the coolant flow rate through all tubes of the radiator equal? Engines with a V layout, or even a W configuration, is the coolant flow rate through each engine bank the same? Here you will once again find that the one with the poorest coolant flow has the largest temperature difference over it. A very undesirable situation. Third question, is the flow rate over each of the engines? Airflow through the radiator, influenced by the grill and number plate placing, intercooler, condenser fan, condenser, radiator cool, fan shroud, fan, engine compartment layout, possible covers under the engine compartment, and undesirable airflow around the radiator rather than through it. Airflow is not the same over the whole frontal area of the radiator. airflow will be higher in the vicinity of the fan and less towards the corners of the radiator and fan shroud. It is important not to have the fan too close to the radiator core, and that the fan shroud not be too close to the core either. Here we have the radiator as viewed from the side, and you'll see that in the corners here and here, the shroud is too close to the radiator. In fact, the fan too is too close to the radiator. This results in low flow rates at the corners here, marked by L, and to a high flow rate behind the fan, which really means that the radiator core is very ineffectively utilized. If we look further at this sketch, we'll see that the radial clearance between the fan and the shroud is too big here, which may result in air actually going in here rather than coming out. If we look at this automatic transmission oil cooler at the bottom tank, the question is, does it influence the circulation from the left-hand side of the tank to the outlet here? If it does, it means that the left-hand side of the radiator will perform poorly because of the lower circulation. You might even find a higher temperature difference between the inlet and the outlet temperatures on the left-hand side. How much air pressure does a fan create? With unrestricted flow, virtually nothing. But the total amount of energy, mainly in the form of velocity, must be considered. Example, if the air velocity is 5 meters per second, then from half rho c squared we get 15 Pascal. Rho's value is of course 1.2 at the coast. If this pressure of 15 Pascal is applied to the air resistance curve of the radiator, the airflow through the radiator can be obtained. The above pressure can also be calculated from the vehicle's airspeed if no fan is fitted. Often the speed through the radiator is very roughly a third of the vehicle's airspeed. Note that the radiator in this case is viewed in isolation and that the role of other heat exchangers is not considered. Over here we have a side view of the radiator once again, with the water flowing from the top down and the air flowing from the left-hand side or the front this way. This axis here represents typical water temperatures for a moderate engine power. We've actually also put in the 30-degree ambient air temperature here. So as the water flows down the radiator, the temperature of that coolant follows this curve over here. You'll see it's not a straight line, so that we refer to it as a temperature glide. Now, the difference in temperature between this water and the ambient gives you your heat transfer. And you'll notice that the further we go down, the smaller this becomes. In other words, we are dealing with a law of diminishing returns. Now, the difference between this inlet temperature and the ambient is called the cooling constant. And in this case, it is 90 minus 30 gives you 60 degrees. So the cooling constant is 60 degrees. The smaller the cooling constant, it means that the system works better. The larger, it's poorer. Now, if we subtract the cooling constant, namely 60 degrees, from this maximum allowable temperature of 115, we get 115 minus 60 equals 55 degrees C. And that is the temperature in which this vehicle should operate safely. Temperature of the coolant through the radiator between the coolant inlet and coolant outlet of the radiator, there is exponentially decaying temperature drop, often referred to as temperature glide. Manufacturers try to keep this below 11 degrees. Here, once again, we have a side view of the radiator with airflow going through it. This axis over here represents the thickness of the radiator, and this axis over here, the temperature of the air as it goes through the radiator. So you'll see that as the air goes through the radiator, its temperature follows this curve over here. Now, since the heat transfer is given by the difference between this air temperature and the water temperature, you see that as you move through the radiator, this gets smaller and smaller. In other words, we are dealing here with the law of diminishing returns, which begs the question, must you use a 2-core radiator or a 3-core radiator? And the answer is a 3-core radiator might have more fins to transfer the heat, but a 2-core radiator may have less resistance to the airflow. So the answer is you simply have to do a test. The temperature of the air through the radiator may enter at, say, 30 degrees centigrade and leave at 70 degrees. Once again, this temperature rises with a decreasing exponential curve. In other words, one has a law of diminishing returns as the air approaches the temperature of the coolant and it passes through the radiator. What determines the top tank temperature? Simply the rate of heat removed by the radiator core as weighed up against the heat the engine produces. Now, throughout this whole presentation, there are two very important statements. Statement number 1 said that the temperature difference between the inlet and outlet temperature of the radiator is only determined by the flow rate of the coolant. And this statement here is the other important one. The top tank temperature is only determined by the rate of heat removed by the radiator core versus that of the engine. What is the maximum allowable top tank temperature then? Typical requirements for petrol engines. Top tank temperature, max allowed, is usually about 115 degrees centigrade. Cooling constant equals the top tank temperature under test conditions minus T ambient under test conditions. And your air to boil is then the top tank temperature maximum allowed minus your cooling constant. I.e., the smaller the cooling constant is, the better the performance of the cooling system. Let's look at an example. Top tank temperature under test conditions may have been 103 degrees centigrade. The T ambient under the same test conditions, 32 degrees. The cooling constant is therefore 103 degrees minus 32 degrees, giving you 71 degrees. The air to boil is the maximum allowable temperature of 115 degrees minus your cooling constant, 71, which gives you 44 degrees. That is, this vehicle should operate successfully in a 44 degree centigrade environment using a 1 bar radiator cap and subjected to its prescribed power delivery. Typical requirements of diesel engines. The manufacturer's top tank temperature varies from 100 to 115 degrees, and often a common 7 bar cap is prescribed. The test is done at wide open throttle, at maximum torque RPM, and at maximum power RPM. The idea of testing at maximum torque is because the pressure above the pistons is the greatest there, but also the water pump speed is lower at that speed, which could be as low as 1500 RPM. And it's obvious that one must test at maximum power too. Special care must be taken not to exceed the engine speed at maximum power, as the injector pump will start reducing the amount of diesel injected to limit the exhaust gas temperature, or EGTs, and thereby decreasing the heat load being tested. EGTs are important on diesel engines because diesel burns slower than petrol and results in hot temperature at the end of the stroke. Typical maximum allowable exhaust gas temperature equals 800 degrees. Coolant in water is water with a percentage antifreeze added, which does affect the boiling point, depending on the concentration. The values below are based purely on pure water as obtained from steam tables. A cap with a pressure of 1 bar will release at 120 degrees centigrade at the coast. A cap with a pressure of 0.7 bar will release at 115 degrees at the coast. A cap with a pressure of 1 bar will release at 118 degrees centigrade at about 1,500 meters above sea level. Improving the cooling performance of a vehicle. Ensure that the engine is properly tuned and that everything that influences cooling is on spec and of the correct configuration. Record the configuration of everything being tested. Increase the coolant flow rate will help because of a smaller temperature glide, and also help because of the higher degree of turbulence of the coolant flow. Increasing the airflow rate will help for the same reasons, but the biggest gain will usually come from airflow side opposed to the coolant side flow rate. The coolant test. This is just a cryptic overview of the coolant test procedure. Ensure that the engine is properly tuned and that everything that influences cooling is on spec and of the correct configuration. Record the configuration of everything being tested. Ensure that the thermostat is blocked in the fully open position, usually 5 to 6 millimeters, but do not remove the thermostat. Choose a day with an ambient temperature near or above 30 degrees centigrade. Choose a windless day and test in 2 directions to cancel the effect of any breeze. The electric radiator fan must be full on during the whole test. The aircon in non-recirc must be full on during the whole test, and while the heater must be off. By means of a drawbar and a low cell, subject the vehicle to an equivalent of a 10% gradient at a speed of 25 km per hour. Measure as many meaningful temperatures and flow rates around the heat exchanger as is reasonable, but the most important ones are radiator cooling temperature in, radiator cooling temperature out, ambient temperature. Measuring the radiator air temperature out could also be a useful indicator. By putting temperature A and C into the formula above, the air to boil temperature can be determined. By working with the ambient temperature rather than with the temperature before the radiator, one gets the air to boil temperature for the larger system, which includes the intercooler, etc. If you found this presentation helpful, please remember to press the like button below.